So far we've talked about three types of Fourier series. And to review what we've talked about, it's helpful to discuss it in terms of both analysis and synthesis. Analysis takes your periodic waveform, f of t, might be a voltage for instance, and converts it in terms of our a sub n and b sub n components. Those are those sine and cosine, our rectangular breakout, or our a sub n, phi sub n components. That's our polar breakout, or in today's lesson, into our c sub n components, our complex exponential Fourier series. The opposite of that is synthesis, and that's taking these a sub n, b sub n components, or your capital A sub n, phi sub n components for cosine and phase, or your complex exponential components, and converting all those back into your time domain periodic waveform. So let's quickly review the three types of Fourier series we've talked about from the synthesis side. And the synthesis side says we're going to recreate our periodic waveform as either a DC component plus that infinite sum of a sub n's times cosines plus b sub n's times sines. And although it's rarely explicitly notated, it's important to realize that the summation is over this entire series. So this top version is called the rectangular breakout, also called the cosine sine or the a sub n, b sub n breakout. And this is the version that's easy to compute analytically, but it doesn't give much intuition. Or the second version, which is much more intuitive, is this DC component plus an infinite summation of cosines. And these cosines will have some sort of phi sub n component to them. So realize that there's two unknowns. There's this a sub n and b sub n, or there's still two unknowns in your polar coordinates. It's your capital A sub n and phi sub n components. Or the third is this infinite sum. Now when we write it in this form, it's very clear how this complex exponential form is mathematically most elegant, even though it has no intuition, and that is because it's a single summation. It might at first appear that this only has a single set of unknowns associated with it, but in fact our c sub n components are complex, so they have a real and imaginary, or alternatively a magnitude and a phase angle associated with it, and so those correspond to these two unknowns. Let's talk about how to convert between these Fourier series. The DC components have a very straightforward relationship among each other. Higher harmonic components do as well. If you write the polar form here in the middle as a polar complex number, it corresponds to these components written like this. Notice that there is that minus sign right up here. And that corresponds to twice the amount of c sub n's. And this is true for n, obviously, greater than 0. And so in summary, these are the equations that let you convert among any of the three Fourier series that we've talked about. Just to give an example, if we're working with these three terms, meaning our DC value and our first two harmonics, and if you're asked to find your c sub -2, c sub -1, c sub 0, c sub 1, and c sub 2 components. In other words, what I would call our center, our DC term and our center 2 harmonics, you can construct them directly. Your c sub 0 is the same thing as your a sub 0, always up here, so that's going to be 4. Your c sub 1 component, your c sub 1 equation from here is 1/2 of your a sub n, phi sub n component. So your c sub 1 is going to be 1/2 of your a sub 1 b sub 1 component in general, which for this particular example is 1/2 2 at an angle of 30 degrees, or 1 at an angle of 30 degrees. Your c sub 2, in the same way, is 1/2 of this value, so that's 1/4, angle of 15. And now using what I described earlier, square shortcut, that gives us c sub negative 1, which you know is going to be equal to c sub 1 complex conjugate, which is therefore 1 at an angle of minus 30 degrees. Same thing as c sub 1, but with an opposite angle. And c sub negative 2 will be 1/4 at an angle of minus 15 degrees. And that's your answer. For completeness sake, since we gave the analysis equations over here, let's give those synthesis equations as well. The first one, a sub naught is equal to 1/t times the integral over any period of f of t dt. Often you don't have to explicitly evaluate that integral. Just by inspection, you can write it down as the average value of your waveform. And then a sub n is equal to 2/t times the integral over any period of f of t times cosine of n omega naught t dt. And that's true for n greater than 0. Similarly, our b sub n is 2/t times, and everything here, I'm not going to write it down, is the exact same, except we're going to talk about sine. So this is the analysis equation for our a sub n, b sub n terms. The complex exponential Fourier series form says our c sub naught is equal to 1/t times that integral of f of t dt, which is, again, the average. This formula is the same as this formula, since our a sub naught is the same thing as our c sub naught. And our c sub n is equal to 1/t, notice slightly different by a factor of 2 than our a sub n's, over any period of f of t, but this time we're going to multiply it by e to the minus j omega naught nt. Same formula as we gave at the beginning of this lecture, and this is for n greater than 0. Actually, it's for n not equal to 0, since this also includes negative n. Notice that there is no analysis equation for the polar form, a sub n, phi sub n. Instead, if you need to compute that, find your complex exponential terms, and then use this equation, just the reverse of this example, to find those a sub n, phi sub n terms.